story today is to look at the two nationalities, the French Lagrange, which we introduced in the last lecture that I've got stacked up on the final screen there, and the Hamilton, the Irish approach to mechanics. And the idea of doing that, the way we're going to do it is to make it clear that one of them is covariant and the other is contravariant. But of course, whenever you write an expression using this fancy GCC technology, you're actually writing an equation that's invariant to choice of coordinates. So when you, for example, write the Lagrangian the way we did, using a metric, we use covariant metric, but we deal with velocity, combinations of velocity with those coefficients. So it's both covariant and contravariant, it's invariant. The Hamiltonian that we're going to develop today using this GCC, same deal, except now we find a covariant thing here, that's the momentum, and we use a contravariant metric. Now just to refresh you on the wall there, refresh your memory a little bit, on the wall here we have the covariant metric defined by the dot product of covariant unitary vectors. That's the one at the top with the index down, and then the contras with their knives up in the air. The contra is a gradient. That's the vector is up in the air. It's normal to the surface, hypersurface, whereas these are along the coordinate line, and therefore covariant is the name that goes with them. The product of the two covariants or the two contravariants gives a metric tensor that, as I say, is very important in physics of gravity, but we're going to make it part of our mechanics. Slight variation, which I'll talk about today, and that is that the mass of the object is included. So, just to remind you, these formulas here are here. The orthonormality relation is here. It won't be until Unit 3 that we get into the covariant derivative. That's a fancy derivative that lets you take account of the curvature of the whatever mechanical system you're talking about. Okay, the main thing I want to get across today is the advantages and disadvantages of each of these. There's no single Swiss Army knife for any physics that I know of, and mechanics is no exception. Sometimes it's really a good idea to use a Lagrangian. I think we made a pretty good case for it by doing the equations for the, well, Coriolis motion, but the hurricane equation I call it, which is the one that showed up down there. So Lagrange has a very quick way to get you to the equations of motion and the physics that goes with it. Hamiltonian and Hamilton equations, not so much, but they have other advantages, and the other advantages are associated with symmetry. The Hamiltonian, very often, in the cases that we're going to be very clear about today, is conserved. The Lagrangian, you see, has underlying in quantum mechanics the phase. Phase is not conserved. Phase is going like mad. That's the heartbeat, I call, of matter, mc squared over h bar, really high. And so it's not conserved. That's not what it does. And so you can't expect the Lagrangian equation always to give you the conservation laws that you need. Hamiltonian, much better at that. And also there's this business of effective potentials. If there's one thing to learn from classical mechanics that everybody teaches, it's that. And so we'll be going over that using two examples, inside the Earth oscillator, outside the Earth Coulomb. We'll see simulations of those with the emphasis on what an effective potential is. So that's the main lesson that I want to get across today. Phase plots are important too. We'll get a little bit into that. as we go along here. Okay, so we've already, just to review things, had differential relations that we eked out of the geometry being on the right-hand screen there, and the equations that go with them for the Lagrangian and the Hamiltonian were in this, on this page in lecture 8, and again in lecture 9. So we're going to be doing more algebraic approach to all of this, but remember, geometry underlies that, so it's worth keeping that in mind. Okay, anything else I need to say about this? The force definition and the momentum definition, those are covariant quantities, indexed down. The covariant G that goes with contravariant velocity, that's Lagrange's. That would be Lagrange's way of doing things. Now this GCC is developed by a completely different part of the world. The German approach, the Riemann and Gauss are responsible for that. So I hadn't quite caught up with Lagrange, and so Lagrange didn't take advantage of that to his disadvantage. Okay, now Hamilton, as I say, is the topic of today compared to that, and we will be comparing them. So let's go ahead and get started with that idea. This being the Lagrange thing that we developed before, and now we're going to do the Hamilton discussion. So how do you derive algebraically all of this stuff that we've talked about that the Hamiltonian does covariantly or contravariant, depending on how you look at it? We need to see that. This is, I'm going to keep all these three screens synchronized for this part where we do the nasty little algebra that goes into the development of Hamilton's equations. It's actually not so nasty. It's kind of tricky, but it's quite beautiful, even as an algebraic thing. Of course, the geometry makes it more beautiful. Now, here we're talking about the total time derivative of the Lagrangian. Remember, I say that's associated with, in quantum mechanics, the underlying phase of matter, matter waves. But here, these people who developed all this didn't have any idea about that until very late in their careers. The idea is to use chain rule to write that thing as a function of q, as coordinate, queer coordinate, and the queer velocity, q dot, and possibly, there's an explicit time dependence. Somebody's mucking with the apparatus that is this mechanical system. So in addition to these two terms involving the time derivative of the coordinate, that's a velocity, and then the time derivative of the generalized velocity, that's an acceleration, a queer acceleration, we need to advance this to the point where you include time as well. Now, the chain rule factor here just becomes 1, so you end up here with a partial derivative of the L. That is the part that you would get only if there was an explicit time dependence going on here, which I'll make a big fuss about very shortly here. So, looking at this, and that's one way to think about it, an explicit time dependence is somebody messing around with the experiment in the middle of the flying of the mechanical system. And here I'm reducing class size. Okay. Something I had to try to do at the beginning of this class as we try to figure out where to put everybody. Okay. That is the idea of making a small class is in this cartoonish way of imagining explicit time dependence. So you're like a mad scientist when you're playing with this term right here. You're catching the thing mid-flight and changing something. So this is what we have set up here for getting the algebra for the Hamiltonian. Okay, the first step in this is to use Lagrange's equations. We're going to use Lagrange to tell us what those coefficients are in terms of momentum. And the idea, as you have already been told many times here, is that Hamilton wants to work with momentum, not velocity. So we're going to have not just the momentum given from Lagrange's equations, but we have the other Lagrange equation here where you take the dot off of the Q and put it on the P, right? Easy way to remember the Lagrange equations. But here we use them in order and replace this coefficient of the chain rule with the P and the P dot. First the P dot and then the Q. Okay. So that's it. That's giving us now the total time derivative of our Lagrangian. And get it up here too. Okay. Now, putting those two first two terms there together, just using the product rule, that is, the derivative of u v dot becomes u dot derivative of v, that's an acceleration, and then u v dv dot, okay, that's a derivative of an acceleration again. Now that's a jerk, actually, right there. In any case, you can rewrite these two terms just as a total time derivative of that product. Now that's something we're going to call the action, or it has a bunch of terms that make up, we call it reduced action later on. So there's an interesting piece of physics showing up right there, and that equation gets flipped, and I've got the expression for Hamiltonian. So that's all there is to the connection between, algebraic connection between these two famous mechanical devices, I might say. But this one right here is got some advantages over this one. But this is a quick and dirty one, and it's the one that you get taught in almost every mechanics class first, and maybe not at all they get doing much with the Hamiltonian. Quantum mechanics, it's the whole story, so when we make that connection, we're going to have to talk some more. But in any case, the idea is that this total time derivative of this quantity right here, that is, the difference between the Lagrangian action and just the raw momentum times velocity action, that difference is the Hamiltonian. And we've got a lot to say about that as we try to make a connection with quantum mechanics. But let's finish the algebra here, because it is rather striking. What a weird equation. The total time derivative of this Irish thing is minus the partial derivative of this French thing, the Lagrangian. That's kind of weird. That's that's bizarre. Now, you should be aware that these equations are all up on the wall there, and we've just gone through the center portion of the main equation set there. So we're making progress in this course here, and I hope to continue doing that. Now, the first derivative. This equation right here, Hamiltonian equal PV minus L, P dot V minus L. We've seen that before. We did it more or less hand waving, but was the geometry behind that was what I was showing on the slides just coming in today. So there it is. That's the Legendre transformation. And of course, it could go either way. I can get the Hamiltonian from the Lagrangian by doing that, or I can get the Lagrangian from the Hamiltonian by switching those two, right? So this is a transformation very obviously going both ways. easily. Okay? Now, what else needs to be said here? The explicit dependencies need to be pointed out. First of all, we've said this many times, explicit dependence of L with respect to the momentum. Triple equal sign 0, identical 0, okay? But a lot of argument was needed to get this, right? This is not something that you just say and then walk away from it. We had to show that the tangents going from secants to actually touching the extrema that required this, and then we did it with the Hamiltonian, okay? So that's the key thing here in understanding the actual Hamilton equations of motion, which are going to be in the lower part of this in just a second here. Okay. Now, what this tells you is that the partial derivative of the Hamiltonian with respect to momentum, okay? In other words, if this is a Hamiltonian, I go here and do a partial with respect to momentum. Well, right away I see partial P with respect to P, and that's true for each component, okay? And this is the case where I've repeated indices on both sides of the equation, so I'm not summing anything at this particular stage. I am here, but when I do this partial, well, it's on both sides, so I'm going to get just plain Q dot M is the partial of H with respect to PM. And that is Hamilton's first equation. Writing it over here. Hamilton's first generalized curvilinear coordinate equation is that guy right there. Let's get it down here as well. Okay? Well, we still go back and what's the partial of H with respect to the coordinates? That's the other thing that we're going to be needing here. And I note, and these are sort of very trivial relationships here, for mechanics, the idea that momentum is independent of the coordinates, so are the velocities. Each of the velocities are independent of the coordinates. So this partial dependency here is identically 0, both of them. And that means when I go through and take a partial of this equation with respect to a coordinate, I get 0 times 0 is really trying to tell me something right here. This is 0, and then I have minus the partial derivative of the Lagrangian with respect to a coordinate. It's what's left. Okay? So that is what gives you this relationship right here, but that is Hamilton's second equation. The one that we couldn't derive because we had no dependency of the Hamiltonian, the energy expression, or the Lagrangian expression. We had no dependency of that on space when we were doing the Superball things, or the very first day, SUV versus VW, right? The idea was that the actual positions of those cars gave no force dependency until they met, and just very briefly then there was lots of dependency of the force on position as they went like that, and maybe popped back if it was time reversible, or just crumbled. Okay, so there was only that very brief dependency on space. Otherwise, we were idealizing it. No friction, no wind, no air resistance, no forces at all, right, on that first dew of mechanics. Well, here we're finally remedying that. Those are the equations of motion that Hamilton is credited with developing. Now there's lots of other people that developed that sort of at the same time. He's the one who gets the credit. That's the way it works in science. You know, somehow you work your way up through the politics and get your name on it. But Hamilton is a really bright guy and certainly deserves credit for this development. Okay, so that's what we're dealing with. The idea is to compare this with the Lagrangian way of doing things. You wouldn't think you'd need two complete ways to do things here. But I do want to point out that this is one of Hamilton's equations, a weird one. Very peculiar relationship involving the partial of L with respect to time, explicit time dependence of L. Is there a mad scientist running the changing parameters in the experiment? If there is, then the partial derivative of L with respect to time will be by clear analogy non-zero. But if you don't, if you leave your hands off of a mechanical thing, make an autonomous system that isn't being touched or messed with by any outside influences, you are then guaranteed that the total time derivative of the Hamiltonian will be zero as this is, exactly. So that's neat. That gives you an indication of what's happening to your total energy. That's what this is going to be. We have to prove that yet. But that's really a key result there. That I pause and let you think about it a bit. It's really worth seeing this and thinking about it. This is a very interesting way of doing the calculus of mechanics. Now, we have to pull this all apart and make equations that just involve velocities or momenta or whatever. Here's one involving momentum that we're going to be using. These are covariant metric definitions of the Lagrangian and P. Okay. Here's the covariant metric that we use. And the idea is to get the Hamiltonian written like that as well. So actual practical applications of all of this beautiful stuff is yet to come here. Okay, let's get that started. If there are no questions. Is this making sense so far, just as a logical piece of algebraic intricacy? Now, a combination of these is really what you need. Legendre transformation is very much a part of making the jump to Hamiltonian. Lagrangian, fairly easy to develop. Hamiltonian, not so easy, as you're going to see here. Okay. So I'm replacing the Lagrangian, and I'm pointing out it is a function of velocity. It's also a function of coordinates, but emphasizing its dependency that differs from that of the Hamiltonian. And so here sits L, and here sits, well, we've dressed this one up. We've shown what P really is. P, momentum, is the partial of L with respect to Q dot. That's Lagrange's first equation. And then we take the L and differentiate it with respect to the velocity, and reduces this quadratic form to a single linear equation involving the velocity, Q dot. Now let me get everything up to match here. Keep these things in sync as much as I can here. Go ahead on that one and this one. So here is what I call an illegal dependence equation for the Hamiltonian. Okay, sitting here with the velocities. That's not what it's supposed to be a function of, but that's what comes out numerically. This is something that's numerically correct. We're going to have to fix that, but right at this particular venture, it's not. Okay, so we take this inverse relationship of the velocity to them, just flip the equations by using the contravariant metric, applying that to P. Basically, that's all that's going on here, but I'm just solving the equation here that expresses the momentum the way it was in the developmental Lagrangian stuff, and getting the velocity as a function of momentum. So I can replace these velocities here with something that involves momentum. And that, the details are on the next page here, but this one is both formally, that is differentially, and numerically a correct equation. This one's true numerically, but misleading, because the important dependency of momentum is really key to using a Hamiltonian. Okay, I'm going to take that one down there up to this point. Here's the beginning of the details of doing the tensor algebra to show this. This is not trivial. It's easy, but not trivial. You have to get used to it a little bit. One of the things that's really key to all of this is that the covariant and contravariant matrix, the quadratic form elements, are symmetric. Okay. And we may notice this on the very first lecture when we talked about a mass matrix. And it only had diagonal terms, so it was symmetric by default. But in general, we're going to, all through the applications that make use of things that are like metric tensors, all the way up through mechanics of gravity, demand that. It's kind of like the demand that the quantum mechanics has for Hermitian operators, and the Hermitian Hamiltonian, but also other matrices that are involving things that are time reversible. They will be symmetric if they're real, Hermitian if they're complex. So here I'm just going through and I'm stuffing the Q dot into this equation right here, and putting little helper lines. Remember I said that when you start to get algebra, it's a little bit more complicated like this is. It really helps to draw a little something between indices that are equal on one side of the equation and therefore being summed over however many degrees of freedom the system that you're dealing with has. So I've got a few of those in there. In here, when I take this thing aside and stuff that thing into here, I'm thereby making it a little clearer where things is, because now there's a big space between that end and this end that have to be summed over the covariant, contravariant end indices involve a sum of whatever degree of the freedom number is. So here's our Hamiltonian almost in the form that we're going to let. But you'll notice that what's happened here is when I put this thing, because we have a minus here times a minus here, and here's where the potential that in the Lagrangian had a minus sign in front of it, in the Hamiltonian it's got a plus sign. Big difference. Okay. That has to be in order for it to be a conserved quantity in the case of no explicit time dependence. Okay, so that's where we're headed here, is rewrite this thing in such a way that I can just collapse it to a contravariant metric and a covariant kinetic quantities, the covariant momenta are sitting there. So that's the result we have. Now, the thing that's a little weird here, and this is why this particular approach using GCC at this point is maybe in question. We are dealing with a metric expression for kinetic energy. We're dealing with the square and some coefficients of that a combination of products of velocities and eventually, and now, momenta. And we have to either have an m or an inverse m if I'm talking about a single particle in some weird coordinate system, and I am, I've got one mass here, and that's, this derivation is just for that one mass. The full derivation of Lagrangian and Hamiltonian, you see, is not in this review unit. I've stuck this in here just to get you the simplest pathway to Lagrange and Hamilton mechanics for one mass. In crazy coordinate system, whatever. Well, not a crazy coordinate. We use the polar coordinates. That's what we're going to actually pull up in just a minute here. But be aware that Unit 2 and Unit 3 are devoted to doing the full job with masses connected and making a trebuchet machine, or you know, all kinds of weird mechanical devices that we'll you know, take looks at later on. But in any case, right now and later on, I will be calling this gamma Mn, and the gamma will be just full of mass dependency, depending on how many masses you have in there. They can all be different or all the same. But that is going to be the way we get to use the full power of the differential geometry of Gauss and Riemann in mechanics. And I think it's really a powerful addition to the way we do these things. But in any case, this is the Hamiltonian we have right now. It has a kinetic part, which is somewhat verbose, but it has a plus the potential. And that is our total energy. And that is formally and numerically correct, and that's what we're after. And if the polar coordinates for the Lagrangian is that, okay, well, it's got to figure, we have to know what GRR is and Gphi. Remember, they are not so simple. They're written on that far screen down there with coefficients for G. Mn is up at the top there. R, Phi, Phi R, and Phi are the dot products of the unitary, and that's something I haven't mentioned yet, is they're called in all of the literature that I can find unitary vectors. They're not unit vectors, so they just put a ARY on that, unitary. They don't mean the unitary you have in quantum mechanics at all. It's a different definition entirely. So do not confuse the name unitary that's used for this stuff with the unitary and the quantum that goes between bras and cats and all that. So anyway, there's the Lagrangian. I'm going to get all this stuff in sync here. There's the Hamiltonian getting ready to come out there, but right now it's the Lagrangian in the polar coordinates using the metric that is up on the fourth screen, the very upper right hand corner there. And actually, I just noticed the matrix is hanging on the edge there. There's a list of the coefficients right there that we need for this. Okay, so maybe I'll put that in the center, back this one off, and that's what we're dealing with. Okay, so this is our Lagrangian, and then it's just a question of how you convert this to a Hamiltonian, where you simply put in the inverse of the metric. That's really easy when it's diagonal, because this is an orthogonal coordinate system, so all we've got is RR and Phi. We don't have R Phi and Phi R, okay? But anyway, we're going to be replacing that minus sign with a plus sign, and we're going to be using the contravariant metric. That's the only change that's in effect here for this. Okay? So there's the only weird term, remember? MR squared omega squared. That was the kinetic part with the rotational inertia. All right. So Hamiltonian comes out looking like that when you make that adjustment. Okay. So we end up here with one more step. That's the whole thing right there. I'll leave that there. Okay, So we've got the radial momentum squared, and we've got 1 over r squared, the angular momentum squared. And then we've got a plus sign on u instead of a minus sign. So there's a good chance to compare, in this simple coordinate system, polar coordinate system, the relationship between the Hamiltonian and the Lagrangian. Okay? All right. Now, how hard is it to take this thing and do all the stuff that we did on the screen, the fourth screen over there, with respect to equations for r dot, p dot, phi dot, and, well, just the equations of motion. That's stuff that came pretty easily here. Not so easy for this. Not so easy. And that's because it got these inverse, contravariant metric coefficients multiplying the momentum. So we're going to go ahead and get through that. Now, main point of this is going to be that Hamilton's equations compared to Lagrangians are more complicated, more algebra, even for this simple polar coordinate system. But I'll point out at the end that Hamilton's equations are in a Runge-Kutta formation. That is, they are set up for a workhorse for numerical simulation is fourth order RK. Runge-Kutta. Okay, there's some Indians involved in this, I think. Okay, and that is a powerful method for doing, well, all our simulations are basically Runge-Kutta. Maybe with adaptive step size for things like Coulomb, which we'll see today, where you really need to be careful as you go real close and get really high values for 1 over r, or 1 over r squared, depending on what you're dealing with. Okay, but Hamilton's set up to do that. Okay, much better, I think, than a Lagrangian. But you can do a Lagrangian too. I'm just making a case for Hamilton at this point, where he's beginning to look a little weak. All right. So let's look at the beginnings of that. The idea being that you need to take his first and second equations, and each one of these has to have something to do with momentum that has the radial component, and then the momentum that has the phi component, and that's going to be related to velocity of those two choices that we have for the two-dimensional single mass in a polar coordinate situation. Okay. Well, first part's pretty easy. Look up here at the h, I can take a partial derivative of p as good as anybody. What I'm noticing here, partial h with respect to pr, okay, this, let's see if I've got that, right here. This is the equation where r is our number 1 coordinate. So this is r dot, this is phi dot. I'm just writing down that first equation, and then the second equation is going to be done with the other parts of the component, angular and radial. Go ahead on that one. Let me keep up. There's the equations that each of those gives. So it's going to just be a matter of taking some partial derivatives for the first part of this. So when I look in there for the partial derivative of the Hamiltonian with respect to PR, it's pretty easy. I'm going to be getting a partial derivative of something squared, so it's 2 times, and then I'm going to get this into the first power, and that is going to give us this little deal right here. I've got this 1 over the mass, you see, so right away I'm seeing here PR divided by mass. Okay. At first maybe that looks a little awkward, but you'll see that it's not so bad. Okay, and same thing here. Now, the next step okay, I take a partial of the Hamiltonian with respect to p phi. It's a little more complicated now. I got a 1 over r squared here, but that's not anything but a factor. I again get the 2 canceling the 2, and get a nice relationship just involving the first power of phi. Now these are partials, so all the other terms that don't have dependency on p phi, they're not playing a role at all at this point. Go on to do it with the second equation of Hamilton. This one, gradient on the coordinate ellipse is equal to minus the p dot here. That's kind of, as I said, a little bit weird. But let's go ahead and do it on these sets here. Okay, and also while we're at it, notice that when we have to take a partial derivative with respect to the coordinate, angular coordinate, we're going to get something as well. Not as much of complexity as this one, though. This one is kind of weird. I've got a 1 over r squared here. Got to be careful to keep track of the extra r's that I'm going to be having here. The 2's cancel again, and I get a p squared, or r cubed. That's kind of weird. Now already you can see, just at this point, and we really haven't done anything but take partials, that this is more complicated than what we were doing with Lagrange, right? Okay? It gets worse. We go and we say, hey, don't I remember that PR is MR dot? Well, that's what I get from these two. Okay, so it gives me something that I have immediately, the very first upper left-hand corner of the Lagrange thing. But you want to check that out. This canonical momentum a little weird, so we want to be careful about that. So that is part of this thing and this thing as well. Next step. Okay, the p phi, all right, where does that come in? P phi here is mr squared times that, well, partial h with respect to p phi is phi dot, so that gives me this little guy right here. So we get p phi equal mr squared phi dot. That was a big accomplishment. We got in one step down there, took a couple of steps to get it here. Okay, well, it goes on. This one right here, okay, same thing. And now I'm looking to see relationships here now with the radial velocity and the angular parts. And I'm going to do it again over there. That one's not so bad. That one comes out something that you recognize immediately. You could have probably written that down first step. But this one in the middle is not so easy. Okay, so you see, here we're just talking about single mass and two-dimensional polar coordinates, and I already got boards full of equations, right? And a few steps where you can easily make arithmetic mistakes. I'm very careless, I think, with my calculations, so I have to go do these things 2 or 3 times to get them right. But this one right here is kind of a peculiar guy. So what we have to do is do an end run around this thing. We say we've got PR equal mr dot. That means if I take the time derivative of that, and the mass doesn't change, that's I said points without saying, I've got a p dot r here equal mr dot dot. Okay, so I can immediately set that just because I have this one right here already in that form. I can get an equation for p dot r from that. But I have to use this guy right here. Okay, stick that guy in there. Okay, and end up with a p dot phi, and there are equations that we got, as I say, at the very bottom with one step in the Lagrangian development. So you can see there's a lot going on here. As I say, now compare it with the Lagrangian result. You can see that just for this very simplest thing, a single mass in 2 dimensions in polar coordinates, a lot more work than just going to Lagrangian. Okay, so 1 point for Lagrange, 0 points for Hamilton. In the secretarial work, you might say, because of this stuff. Okay, there's a thing we're comparing up here. All right. Now, just to pull something out for poor old Hamilton, he's feeling kind of bad. This guy's in Paris who's beating his ass. What can we give him? Well, I can give him this. And this doesn't happen for half a century or more from when he lived. And that is that we have computers that can rip through something like that. That's the Runge-Kutta setup. Okay. So just equations involving the positions or whatever. If you've got first order differential equations set out in such a way that you've taken apart, obviously, some second order differential equations, or maybe higher orders are at work here. But in any case, we can rewrite this very nicely in terms of r dot, pr dot, phi dot, and p phi dot, and then presumably have equations immediately for each of those. We're in business. We can just work that, and this is the polar coordinate form right here. So I hold that up as something that we kind of do all the time in our business here. And you'll be seeing simulation that is essentially using this. Okay, now something else. This is where Hamilton shines. This is where it really makes a big difference. And this is where we'll see the simulations that go with it. Both for oscillator, that's inside Earth, inside sophomore physics Earth, and while we're at it, we'll do the outside orbits as well. The hydrogen, kind of Hamilton mechanics that you would do if you're doing semi-classical mechanics of the hydrogen quantum mechanical problem. So that's very much in the offing here. Okay? And the reason it works is because of conservation. First of all, if h is not an explicit function of h, this would be true for Lagrangian too, but here we get to make use of it. If in fact the second equation of Hamilton notices no explicit dependence in the angle phi, that means the thing has a cylindrical or even spherical symmetry, we're in zero land for the partial derivative that's causing us to have a complicated equation involving this Hamiltonian. So if h has no explicit dependence, it has symmetry. Symmetry, S-A-M-E-T-R-Y, okay? It's always the same in all different angles, okay? No partial derivative with respect to phi. I've got no change in the angular momentum, p phi. P sub phi is fixed, a constant. Now I use the atomic notation very often used for angular momentum, L. Now that comes from the letter L for Lagrange actually, but that's just a little bit of history. So what we can do here is go through and take the entire Hamiltonian, which has two kinetic variables and two angular variables, one of the angular variables out, so that makes one of the kinetic variables into a constant. And there's a name for that. That's called the effective potential. Now this is true not just for the Coulomb problem of the sophomore physics Earth outside, not just for that, but for any problem that only has a radial dependence. It doesn't matter what the radial dependence is. This is going to work. Okay. You're going to be able to take the real quote-unquote potential. You're going to be able to take that and add it to something that is involving the angular momentum constant and maybe some more functions of r, but that's it. That's going to be an entire effective one-dimensional potential. And there's a name for this. It's called the centrifugal barrier potential. It goes to the quantum mechanical scattering problem that came up after all of this stuff got used for quantum mechanics. So this is a real plus for using Hamiltonian, that you can do this fairly easily with some pretty complicated machines, like a trebuchet, which is what we'll be using in Unit 2 to develop the most complicated Lagrangian algebra that you could possibly have, and still be able to live through it in academic terms. So once you get this, you're then able to solve for the radial momentum. And as I said, this is true for any UR, not just the oscillator, which we'll treat, or the Coulomb, but you name it. Now, it may be quite pathological. You may get all sorts of very weird mechanical effects, quite beyond what the oscillator and the Coulomb think. So they have hidden symmetry that most of the functions of U, functions U of R, would not in general have. So it's quite easy then to go ahead and solve the momentum, how fast the thing is going in the radius as a function of the radius, its closed form. And not only that, but in this case, and it's pretty much true in cases related to this, you can integrate the results. Now, we won't be doing that until we're in the middle of Unit 2. And then I'll do both of these together, the Coulomb and the oscillator, right on top of each other, show the differences in each state. That's really fun. You see some very strange symmetries sort of popping out if you look for them carefully. But right now, I just want you to see that we have an integral here for a potential, and I'm thinking of the oscillator potential, kr squared, that has an integral that looks like that, and the Coulomb is kind of related to it in a funny way, but we're anyway, when you do this, when you reduce the thing using an effective potential and the Hamilton giving you some extra conserved things, that is beyond the energy, which we know is a constant, but in another constant of the motion. That's cool. What you do is, this is called reduction to quadrature in the literature. It's called a quadrature or quarter cycle, is really to say, quarter cycle solution for some oscillatory mechanism. You're basically going from a low value of the radius to a maximum value. That is, you're going from the perigee, the low point in an orbit, to the apogee, the maximum amplitude. And that's usually a quarter of a cycle in some sense, a quarter of the motion and quadrature. That's the best etymology I can give you for the name reduction to quadrature. Okay, so that's an integral we'll play with later on. That's the one that's going to give us the geometry of Coulomb orbits as clearly as the geometry of the oscillator. But we're going to spend some time looking at both of them here. Now. Okay, so that is the end, for now anyway, of the algebra discussion relating this Paris versus Dublin, okay, French Lagrangian approach versus the Hamilton Irish takeoff mechanics. Okay, is there anything in your mind? Is it all making sense? And we could have a midterm right now, and you'd be able to write all this down, right? Yeah. Well, that's that's where you should get to. I mean, this is kind of stuff that you should be able to put together. As I said, you should go and be able to go home and derive the Lagrangian equations just from scratch. think what it is, the logic that went into it, and just come up with that. Because when you do that, that will really cement a lot of this stuff. Otherwise, it's in one ear and out the other when you don't use it in some way. You don't get stronger by watching somebody else do push-ups. That's what they used to say for gyms. But here it's true too. It's involving the muscles up here. Right? Okay. Well, let's take a look at the effective potentials for the oscillator. Okay, this harmonic oscillator. See, what could be so hard about a parabola r squared? Well, what could be so hard is that the angular momentum, if it's not zero, involves an inverse r squared. The centrifugal barrier, the barrier that keeps you from, when you have any angular momentum at all, it keeps you away from the r equals 0. So there's a typical effective potential for an angular momentum. I'm using mu now for the L. Here's mu equals 0. You can go, if you've got mu equals 0, you know an oscillator likes to go through the center, right? Can't do it here. And of course that has great quantum mechanical significance. It means a wave function has to be absolutely 0 for anything that has an L not 0. Can't be any part of there at all. And that's a wave function that's everywhere else, right? So that's the key thing. The centrifugal barrier completely makes it avoid the r equals 0 point. Well, there's an evanescent wave, right? But that's 0. That's 0 too. Okay? So that's what we want to play with. And here is a picture of an orbit. And it's hard to tell, what all is happening here until we animate this one. So we're going to be splitting the screens up now and do some animation. I think we'll do it on the middle one. We were having issues with complete drawing of these orbits, but let's go ahead and get this one going there. We get to see some of these effects, the effective potential and its centrifugal part playing a role. Okay, so I'll bring this one up to that point, and I will start. Let's see if I can get the simulation going here. This is the oscillator PE. Yeah. You can see that this is really quite an oversimplified picture of, first of all, the x and y coordinates that are making the ellipse that this is what we constructed by ruler and compass, right? And of course the idea is that this ellipse could be at any orientation, so orientation is completely ignored by the effective potential diagram, this one. It's not taking into account the fact that there's a world outside of a plane, and the idea is that the plane that you have here is literally rotating around depending on where phi is. Okay, so that's one thing to notice. So this thing goes from perigee to apogee, back to perigee, back to apogee. It does 2 trips, perigee to apogee, in one orbit. Exactly. So that's a very specific symmetry that the oscillator has. When we look at it in polar coordinates, we comment on apogees, perigees. There's the apogee again, and there's the perigee. So reaching into this region right here, one of the things I can do is just bring this thing pretty much to a stop. Well, I didn't quite get it. It's still oscillating just a little bit. I didn't quite get the bottom of that green curve, which is the total effective potential. But it's close enough that you can't tell this from a circle, right? It's not moving its radius very much at all. It's an ellipse. Well, a circle is an ellipse too, but this one is an imperfect circle in a sense. It's slightly elongated. So it has a, I think that's the apogee, and then the perigee is coming up. But you can't see it very easily. In any case, if I just go up here and just pick a random position of the thing, let her go, well, this diagram is going to look the same for any ellipse of that orientation. And you'll notice when we plot px versus py, we're getting pretty much the same curve as this one. Remember how we studied the calculus of the two-dimensional oscillator and noticed that the ellipse for velocity was the same ellipse as the position when omega is equal to 1. Now omega is not equal to 1, so one of them is bigger than the other, but still the same orientation, right? That's kind of neat to see.
Mr. Harter, they appear to be a quarter out of phase as well.
And that is what you notice. It just went, this one went by its perigee when this one was at its apogee. There it's happening again. Zooming by there while that one was reaching its peak. That was the other thing we noticed, or pi r 2 out of phase, right? Thank you. Okay, so, you know, no matter what you make, you can go clear up here and have it go way out there. And then it comes back again and goes BAM! Off a really hard wall here. And that bang is right now, just as it passes its perigee. And then it takes its good old time while it's up at the apogee. It doesn't turn around very fast, right? Meanwhile, we can do plots of other quantities here versus time, and they're basically not interesting oscillatory plot. They're just sine, basically sine or near sine curves. Okay? All right, well that's the inside the Earth motion, and the neutron starlet particle going around inside a isotropic oscillator. Let's see if we can get something else going here. This is effective potential and orbits for the oscillator. I want to see if I've got here Coulomb. Yes, I do. Okay. So this is what we're going for right here. Now I have to back out of this one. I'll make sure that I'm not using CPU unnecessarily, because run the code is fast, but it's eventually got to give it some more, give it some computer time. Let me go ahead and back out of this, go forward to the Coulomb one, and see what that looks like. I think we can get that started here. We were having some trouble. Yeah, here we go. Now there's some surprises here in this plot that we will explain later on in Unit 3, actually a little bit in 2. But really Unit 5 is where we mentioned that bizarre behavior right there. Plotting px versus py gives a circle. It's always a circle. This can be a circle. You can have a nice circular orbit in a Coulomb field by being at the bottom of a particular effective potential. And I'm trying to see if I can get this thing to that point. I'm not quite there. Again, this is a little bit elliptical, but that one's still a perfect circle. Anybody ever been taught that that's what a momentum does in a Coulomb field? Have you ever seen that anywhere? You should have, he says, with 20/20 hindsight. That's really cool. I didn't notice that until we got a simulation. As you make more eccentric orbits, I forget where this one has the position velocity clicking.
It should. Just
Let's
click
see
and
if we
drag.
Let's see if we can get a. I'm having a little trouble with my cursor here. We'll see if I can get a nice eccentric. You see, one of the things this thing does is show you where your effective potential is a little bit. I don't want to throw the thing out of the thing. I'll bring it down here. Let's just try an ellipse like this for the heck of it. See what happens.
Okay, that's bound.
Here we go. Watch that circle. It's taken a long time to get around the apogee. And now it's starting to fall. It's starting to fall. It's going boom around the circle, right? Isn't that cool? So this is the outside the Earth guy, but it's got that geometry. And these guys are kind of bouncing along here. Isn't that
Lost a little bit of energy.
Pardon?
Our orbit was just a little too close. The algorithm lost some energy on each of those
Yeah,
passes.
you can see that happening. You watch the energy here when it does the next one. See, it's very happy out there on the extremes of the Coulomb, where it's very flat potential. Very, very flat force square. I didn't bother to draw that. But when you come in there, bang! See, I lost a couple of points on the energy here. That means the Runge-Kutta needs to be step size dependent, which makes it not quite real time. That's what the price you pay if you're doing simulations for visualization. Okay, so I think that is a neat message there. Starting to think in this region, same deal.
Yeah, a little bit of loss.
And I see I'm losing it in the third figure every time on that one as well. But that basic idea of what's happening is present in both of these. Okay? All right. So centrifugal barrier for Coulomb, pretty important as well. And barrier here, but it has a well. And finally, as you get up to escape velocity, then the curve becomes repellent and no closed orbit. You get a hyperbolic orbit. We'll worry about that stuff later on, but this is enough, I think, to see what we're up against here. Okay, let me back out of this. There are a couple more things that I'd like to show before we're done with class today. I want to remind you of the 3 steps to heaven, or going the other way, the 3 steps to hell. Remember that as we talked about the geometry of the plot that makes a change from the Coulomb potential to the oscillator potential right at the surface of a uniform sophomore physics, or a uniform sphere. This would be true for a uniform charge density as well as a uniform mass density in the green region. Okay, so I want you to, once again, and we'll play with this more later on, this is part of the symmetry of the Coulomb business. Back in lecture 6 we had this picture here, and go ahead, put the thing on the other screens here as well. So it's the 3 steps from sitting inside at the bottom of the harmonic oscillator potential and asking how much energy it takes to get to be sitting on the surface of the object, whatever it is. How much does it take to get orbiting in a circular orbit at that altitude? That's this dot right here, and that's an equal jump from here, and then finally to just get out of here, be gone, and be sitting at 0 velocity at infinity, whatever that means. That means you're out of here. That's another jump of the same amount. Okay, remember this? Okay. And probably worth noting what the extreme cases of that were. First of all, there are all the formulas that we worked out in that 3-step problem. This is again lecture 6. We're going to be doing that all over again later on, maybe a little more elegantly. And we also talked about crushing our sophomore physics Earth, and the lessons there, I hope they made some impression at the time. So that is what we have to work with. Now, the question is whether we can use the next few minutes here to take care of some things that I would like not to have to spend too much time with on the next lecture, where we try to make connections for our Hamilton, Lagrangian, and quantum mechanics. So what I'd like to go ahead is, I say normally we'd stop right here, but I would like to just tell you a little bit about the pendulum. Now there's another kind of pendulum that I call a cycloidulum, or something like that, and that's what we'll spend some time on in lecture coming Thursday. And we also talk about a little bit about what I call the Jerkett system. That's parametric amplification is a big deal for that. And I have something called catcher in the eye. I might be able to show a little bit of that right now. But mainly I want to look at the pendulum. The Hamiltonian for the pendulum is really quite beautiful. And these are the 3 geometries that you would use to consider. First, the force. Every sophomore physics textbook has the very first one there, just asking what does gravity do? Well, it pulls that much force in this direction. No matter where you are, it's always hanging straight down. But its component, in terms of how its effect is felt, this particular force right here will have its maximum right here, will be absolutely 0 right here, and that's just a sign, a projection for mgx, x being r sine theta. For small angles, just r times the angle theta for small oscillations. Okay. But this is not a harmonic oscillator for anything but the small angles. So we're also interested in the energy geometry. This is where we figure out what the height is. That's a Thales rectangle problem when we talk about the superball being compressed, but that's what we're interested in. What's the energy effect? And then finally, the time geometry and the elliptic functions and all that come out of this. And that's something we'll study later. But there are the 3 geometries that make us have this particular Lagrangian. Now this particular Lagrangian has a Hamiltonian to go with it, but I want you to notice very common loci, locuses, for plus and minus sign blunders. The potential here is a minus cosine. The idea being that as I go up, I should have for my small angle thing, I should have a parabola that's like this, but a cosine is like this. So I got to turn the cosine with a minus sign down like this, so I can have something that sits at the bottom. That's what my potential is. And therefore the Lagrangian, which has a minus potential, has a plus sign here. But the Hamiltonian has got a minus sign there. Okay, so in dealing with that, a couple of sign flips here that could easily throw you. Now, I don't need to make a big fuss about this anymore. We don't have a qualifying exam anymore that makes people make mistakes like that. But still, you could make a mistake like that before an important talk, somewhere where you would have gotten a really good job if you hadn't screwed that one sign. So, the warning is, I hope, taken. Okay, there's lots of ways when signs are being flipped a lot that you want to understand the problem well enough to say, yeah, that's the right sign, I'm not worried. In any case, this is what we have to solve, and this is what the Hamiltonian looks like. This is a case where you simply plot the Hamiltonian h of p phi, or theta, I'm using theta now, okay? That's in this direction, and then the cosine of theta with a minus sign is in this direction. There's a bottom of the minus cosine right there, going to the top right there, and then back down again, and forever and ever, all the way down to Fort Smith, and up to Bentonville, we've got this cosine curve, right? And every time you go over the pass, you see, there's a set of lines there that mark the outside of a phase diagram, which shows all the possible trajectories here, with a velocity that's getting faster and faster and faster as we go up this side of the mountain that never comes down, and up on this side another mountain that never comes down. Okay, and then there's another ridge right here that never comes down. That's its bottom. That's a saddle point. Okay, so there's this topology of a anharmonic oscillator. That's what we're dealing with this Hamiltonian. Now, there's a couple of ways to look at a Hamiltonian, and let's go ahead and get this picture. It doesn't show very well there because of the defect in this particular computer, which I have not yet had fixed. But you can look at it either side of the room now, and I might as well go ahead and put the rest of the equations of motion. They're really quite striking, these Hamilton equations of motion. I can see the thing there. Basically, it's q dot equal partial ph, that's first equation, p dot equal minus partial respect to q of h. Well, that's a cross product of a gradient of h. So what this is telling is, when you have a high gradient, you've got a lot of something that's making you move. If it was just the gradient in this direction right here, you know that's the force toward the center. But when it's the gradient on this line right here, it's telling you how fast you're going to go by when you go around this corner here. You're going to go really fast because it's really steep there. You're going to slow down here where the thing is not as steep, and so forth. So what this is telling you is it's EH, that's the unit vector along the Hamiltonian axis, cross the gradient with a minus sign. And so what you do is you take your left hand, you take your right hand in this case, I'm thinking of my rotors. You take your right hand and put it on the Hamiltonian axis. I'm sorry, it's your left hand. It's got to be. This is a phase space. You put your thumb up the axis there, and that's the direction that you go in the phase space. The kind of easy argument for that is when you're, I'm up here on this side where the momentum, that's the phase, angular momentum is high, I've got to go positive. So this has to be left, just like our phasors oscillate. Okay, and the phasor that's a circle is you know, very, very close to a circle is down at the bottom, but here they get to be very weird. So that's what I would like to show you a simulation of very quickly for that motion. See if I can find it here. I may have to go back and pick it off of the menu here. Yes, I have to go get it right here. Now you guys can look at the others and you'll be ahead for the lectures. But here's a picture of something going around that. Now I'll start off at the bottom of the well, okay, right here. And that'll make a cosine curve of a frequency that's a lot faster than the one we just saw. And then I go a little bit higher here, you see, to 1, and start it again. And you can see that that is a slower frequency. The cosine's fatter than the original one. And if I go inside that circle, you won't be seeing much of a difference. You can see that you don't see the divergence to get, you know, out to the end there. And the closer I get to the center there, the closer I get to being a harmonic oscillator. I was a little sloppy in the placement there. But when you go out very far, then you start making things that really aren't cosines anymore. They're elliptic functions. And the science and mathematics of elliptic functions is really quite beautiful. And this is something that Brad Clay has taken as his project to study the mathematics. Whoops, I went too far. I've got to actually look at this thing right here, see if I can get one that doesn't. There we go. Now in quantum mechanics of Bose-Einstein condensate, these functions are actual wave functions, and they're functions that go a long way before they go down, then they stay a long way, and then they come up. Really incredible functions. And they're wave functions for DEC. This is something Bill Reinhardt and Phillips discovered not too long ago. Anyway, that's the phase space. Now the rest of the phase space, of course, when you go here or here, you approach this rotation, uniform rotation, but here it's kind of non-uniform rotation. It slows down at the top noticeably, but the rest of it is an inside job, and there's periodic, but not harmonically. This is not harmonic. Question is, how do you make this harmonic? How do you save physics? And the answer is on the wall back there in the corner, and that's what we're going to look at next time, among other things. That's a Huygens pendulum. Huygens, the guy that made the Huygens contact wave thing, brilliant person, But it took until he was just about to die and he figured out how to make pendulums really precise using cycloids. Save physics. Physics, it didn't look like physics was working. The clocks really couldn't keep time. Change the amplitude, they slow down. Okay, we'll see you on Thursday with that and some other things that relate to quantum.